concrete. Portland cement concrete. When people talk about concrete, they mean normally PCC. There are more details in chapter 7 of the textbook. And since you won't do a homework on concrete mix design, I encourage you not to miss a class because there will be one mix design question on the exam next week. I plan to solve a number of examples in the class, and I hope that we work on the examples together, and then you are all good and up to speed with the mix design. Clear for everyone? So the mix design is, you want to find out what is the proportion of each of the components of concrete. What do we have in concrete? Aggregates, fine and coarse. We have what else? The sand is fine aggregate. We have water. What else? Cement. What else? Admixtures. What else? There is also some air in concrete. And you'll see that even we need to design for the amount of air voids. So we followed the procedure in American Concrete Institute, ACI. And basically, this gives you some sort of the procedure, starting from the mix design. Then we do, afterwards, as engineers, you do trial mixes, batching, and that's when you start mixing. And remember the cement hydration curve? This is when you start the clock. Then you have to transport the material to the field. Then you have to place it. And then you have initial setting. You have to do vibration. Final set, before final set, you need to do finishing. And then you cure the material, and afterwards maintenance. So this kind of gives you the whole concrete design and construction steps. Today we want to focus on the first part, just the concrete mix design. And typically what we do is you design the proportions for unit volume. So unit volume could be 1 cubic feet, 1 cubic yard, 1 cubic meter. So you design everything. For example, you design to have 290 pounds of water per cubic yard, or 760 pounds. Everything is understood that this is per cubic yard. And 1 cubic yard is how many cubic feet? How many? 27. This is useful. You will see that sometimes you need to not to forget that. So we follow the step-by-step ACI method, and we focus on one particular method. We don't do everything here, of course. So what you normally do, you calculate the first approximations and then you correct it. Now, this is the step-by-step procedure. And for the exam, you could have this procedure written down in your cheat sheet, your formula sheet. You can write these steps, and you can bring all the tables, or the textbook, actually. You also have the, if you want to bring the textbook, it's fine with me. You cannot bring your notes, but you can bring the textbook, and you could bring this step, you can write these steps down in your formula sheet. I don't want you to memorize that. So these are the steps, and what I'm going to do today is kind of go through that with you in an example. Before that, we need to learn a few things, and then we'll start with an example. So, and you look at the steps, we go back to that. I don't need to read this for you. Before going to the steps, there are a few things which is useful to have handy. For example, specific gravity of water and cement. Also their unit weight, as you can see here. Some other quantities like ton and gallon. What you need to know before designing a concrete mix is what this concrete is being used for. For example, you need to know what is going to be made out of this concrete, what type of a structural member it is, and typically the structural engineer gives you a design strength. You need to target a particular strength. Another very important criteria is to know what would be the environment. Is it going to go for a project in Arizona or Pennsylvania? That makes all the difference in terms of exposure. Also, the how corrosive is the environment, or exposure to sulfate, for example. There are sometimes some job-specific requirements. For example, it may you may not have aggregate size greater than or less than a particular size. Maximum allowable water to cement ratio may be given, etc. You will see. So there are some other inputs. In terms of material, we talked about it. A lot of times you need to use local materials, so you may have some constraints on what you have available. Of course, also in terms of cement. If there is a cement plant nearby, you kind of want to use that type of cement. So that can shift your design strategy a little bit. Sometimes also you want to, there are some constraints on the supplementary cementitious materials that you can use. A few things, I put everything in this package so you don't have to go back to aggregates, for example. A few things to kind of remember. Remember we have talked about, for example, oven dry rodded unit weight. Remember that we have the aggregate weight, and this is based on the apparent volume. You will see that the coarse aggregate design is based on apparent volume. Some other things that I hope you remember are these different states of moisture for aggregates. Remember that if the material is not saturated surface dry, then you need to correct the water. What you get from the design tables for water is assuming that the material has SSD condition. If your material is air dry, you need to accommodate it by providing a little bit more water for the aggregates to reach SSD. If it is moist, then you have to take into account this water that will be released in the mixture. We have talked about it before, but it's kind of review. Another parameter that you have seen before is this fineness modulus. Remember, it is the weight retained on a number of sieves. And so here, for example, you have the sieve analysis. This is person passing. The definition of fineness modulus is based on person retained. So the higher it is, means that the material is coarser or finer. The higher fineness modulus means the material is coarser or finer. It's coarser, right? Because it's person retained. Okay, so these are the kind of introductory material. Also, it's helpful when you do the examples to go back and review. And this is the example that I want us to work together and go through these different steps that I listed in the beginning. So let's read this together. You want to design a concrete mix which has a 28-day compressive strength of 3,500 psi. So why I'm talking about 28-day strength? What is the number 28 coming from? Why it is saying 28-day strength? I'm sorry?
Like 28 days standard rate?
Right. Why 28 days? Why it doesn't say 35 or 15 or some other number? Very briefly, I've talked to you about this last time. What happens?
How long concrete takes to develop most of its strength.
Right. Remember I showed you a graph and you could see day 3, day 7, day 14, day 28. And I told you that concrete gains the strength with time. So as you cure it, it becomes stronger. And we assume that by 28 days, most concrete types, they have achieved around 85% of their strength. So that's where the 28 days come from. You hear this all the time. So 28-day compressive strength, and the concrete is being used for a precast culvert. You have the dimensions with 8-inch wall thickness. So this is the function of this concrete member. Remember, in the beginning, I told you when you design, you need to know what this is being used for. And you'll see in a minute why. Because in the tables, you have to look for the right type of a structure. And reinforcing steel bars will be placed with clear spacing of 6 inches. Cover is 1 inch. Everyone knows what cover is? When we say cover? So if you have concrete members, you have reinforcement steel inside. Cover means how much concrete you have over the reinforcing steel to the surface. So that means that this is 1 inch. And clear spacing between the rebars is 6 inches. How far are the rebars? It could be center to center spacing. This is clear spacing, means that it's not center to center. So this is about the structural member, and then you learn about the exposure. So you have severe freezing and thawing in a moist condition. Sounds a little bit like a state college, right? Concrete is exposed to moderate levels of chloride and sulfate from brackish groundwater. So you have both chloride, it could be from salting, de-icing salts, and sulfate. Okay? And here, you have some information about the aggregates. So now you have to kind of download the information in your mind that you have about aggregates. You should be able to understand what is given to you. Like MC is moisture content, absorption capacity is what, dry rotted unit weight was what. So that's why I was revealing this for you, very bulk, specific gravity, and so on. So the first step in the design is to assemble information. So the first step is to kind of make a table and write down the information. So I go back and I let you go back to the problem and try to assemble this information for yourself. So work with your neighbors. Try to do that. So you basically summarize the information that they're given in the design problem. function is what this is being used for. Strength is clear. Dimensions, whatever is given, you see that you need all of this information. Exposure, and then materials properties. Materials properties is here. So try to make a little table for cement, for fine aggregate, coarse aggregate, and write down the information that you are given. Moisture content, absorption, density, specific gravity, whatever you have, put everything together in one slide, in one page. No. Dimensions of the member this concrete is going to be used for. So look at the dimensions that are given in the problem. Because where is the problem? It's the arrangement. So make a little table at the bottom with different properties for different materials, right? So you have cement, fine aggregates, coarse aggregates. And pay attention to what you are given. Dry rodded unit weight is based on apparent volume. Bulk specific gravity is based on absolute volume. These are different things. So make sure that you have columns and you put things, moisture content, absorption for each material. And if you have forgotten, moisture content at SST is called absorption. So this is what I have. It may look different, your table. Don't try to erase it, and it doesn't have to look like mine, as long as you have all the information included. I don't have all the dimensions actually written up. So yours may be better than what I have there. You should cross it, no. The thing is always the smallest dimensions all the time, so that's what you like it, but you should write as much as possible. So this is kind of the first thing. It doesn't, this is not very difficult, but if you have it, there is no more. You can just no, this is the culvert is like a channel that carries water, if you don't necessarily know what it is. Okay, feel like most people are, when the noise level goes above a certain threshold, means that you are ready to move to the next step. So look at the steps here. So we are done with the step number 1. We move to design on slump range. I hope that you looked at the 20-minute video and you know what a slump is. Is there anyone who wants to define a slump for us, for the class? What's the measure of a slump? Is the measure of what? Yes.
Change height of the
Exactly. So you have a cone. You turn it upside down and you measure how much the material is kind of going down. It's the measure of what property of concrete? Why do we do that? Exactly, workability. That's what you need to think about when you think about a slump. This is how it looks like. Sometimes you kind of know it's given to you. If it's not given to you, there is a table where you can kind of decide on the slump range. So you see the tables, I'm giving you where they are in the textbook. But we can also print out the tables that you have in the notes and bring it to the exam. Either way is fine with me. And we don't see any culvert here. So here is kind of the function, and here is the range of the slump that the code is suggesting. And culvert is, the closest that you can look at is like having a beam or column. And you see that the range is pretty wide. It's from 1 to 4 inches. So we go with the highest range, but you could have chosen something smaller, like 3 inches. This is where the art of design comes into play. It's a design problem. So I've chosen 4 inches. So you see the maximum, minimum. In the numbers are in millimeter and in inches, as you can see here. So another thing that in the 20-minute video you have seen is water reducer. If you use water reducer, you can increase the slump. So coming here and going counterclockwise, you see that, actually starting from here and going clockwise, you see that, okay, this is the normal one. Then you have, and you just add a little bit of water reducer. Here is the mid-range, and this is when you add super plasticizer. So it helps increase workability without changing the amount of water. And this is kind of the percentage of water content reduction for the same value of workability for different ranges of water reducers. So you go from normal one, 5 to 10% to 6 to 12%, and then super plasticizers, they can reduce the amount of water by 30%, up to 30%. So that's something to keep in mind. So now we decided that we want 4 inches. The next step is to decide on maximum size aggregate. Remember that in the gradation curve, what that is? Now we have to decide on that. This is a design problem, so again, the code has some provisions. And here is where you need to use the dimensions of the member that you are designing. So these are the criteria. It has to be less than the narrowest member dimension divided by 5. Less than, this is not the unreinforced concrete slab, this doesn't apply to us. If it was, you would take the depth divided by 3, this doesn't apply to us. Clear rebar cover, this applies to us. Clear rebar spacing, this applies to us. So try to design for the maximum size aggregate based on the dimensions that you have. You have the cover, you have the spacing, you have the member dimensions. See what you should choose for the maximum size of aggregates. And here is some sort of visual way to show you the rebar spacing, what it means, the maximum, the dimension between the forms, and if you have unreinforced concrete slab, this is the depth. It's kind of obvious, but so let me see what you get for the maximum size of aggregate. Look at your summary slide and see what dimensions you have. So the way to do it is to apply all these three criteria which are applicable and then decide on what to choose. So that doesn't apply to us. The narrowest member dimension is how much? 8 inches, right? That's the thickness of the culvert wall. So this is one criteria. The other is it has to be less than clear rebar cover, which is 1 inches. And also, it has to be less than 0.75 clear rebar spacing, which is 6 inches. So now you have all these criteria. You have to see which one controls your design. If it has to be less than 0.75 inches, less than 1 piece of 1 inch, or I don't know exactly what this number is, which one would control? If it has to be smaller than all of that, this is the smallest, right? So we need to choose that. So then you say, okay, I designed my MSA to be 0.75 inches. You see, this is a design problem, so there is no like correct answer. You could choose 0.5 inches. But you normally want to choose the largest aggregates possible because that makes your design more economical. It's cheaper. The more aggregates you have, things are going to be cheaper. So this is what we are going to choose here. And that's what I want to show you. So if you have larger aggregate size, you need less and less cement because remember the surface area will be less. You need less glue, right? And less cement means cheaper concrete. That's why you kind of go with the maximum. But it's a design problem. If you have a very wealthy client, you can go with a little bit lower. Normally we don't do that, right? So we are done with this step 2. Now it becomes more interesting. Now that we have this, you may even want to, for yourself, write things down so you don't have to go back every time on a sheet. Then we want to find out what's the amount of water and air content. So how do we find out? We need to know the slump and MSA to be able to find out the amount of water. You also have to have an idea if you are going to use air-entrained or not. When do we use air-entrained concrete? When do we need it? Why do we use air-entrained? Exactly. You want to prevent freeze-thaw damage. So if you don't have air-entraining agent, for example, this never happens like in a climate we have here, right, in PA. But if you don't have it, this is kind of the table that you have. It's very important to read the details in these tables. You see it is water, pounds per cubic yard of concrete. And then here you have slump range, and here you have MSA. So you need to know both of them to be able to figure out. And remember, this is the water, assuming that the aggregates are SSP. So the aggregates are not going to get anything from this water or give anything to it. That's like the important point to remember. Most of the time, we are going to use this table, which is for air entrained material. Look at this table. Based on the information you have, design your water. And remember, this water is assuming that your aggregate is SSP. It's not going to steal any water from you, and it's not going to give you any extra water. And then you also have in the red part, you also have the percentage of air voids. Again, you have to know the exposure, and you have to look at what you have chosen as MSA. So this is again MSA. This is slump. This is air content, the red. And you see the reference to the, in textbooks you have all these tables. Also you can look at the total. Okay, choose your water. also need to choose how much air content you want to have. Write down the units too. Pay attention to the units to pound per cubic yard. Why do I say cubic yard? Remember in the beginning I said we design for 1 unit volume of concrete. Then if you have 1,000 cubic yard to deliver, you just multiply everything by 1,000. It's as simple as that. This is easy, right? We have 3/4 of an inch for MSA, 4 inch for slum, and severe exposure. So if you were going to use air and training admixture, then you kind of need to take this into account. We are not going to do that in this class, but that's kind of where you have to look into to make sure that you achieve this kind of air content. That's the definition of different exposure. You can take a look at it. So we have water and air content. So sometimes you can reduce the amount of water if your aggregates are angular. You remember when I was teaching you aggregates, I said if you have angular aggregates, they help workability of concrete, so you can reduce water. And this is a table which tells you that. Here we don't have any information, but if you have, you can take this into account. So you see if you have, let's say, round aggregates, gravel, you can take 45 pounds per cubic yard off your water. Also, if you are using water reducers, then depending on what kind of water reducer you are using, you could reduce the amount of water. That's another point. So, we are done with water and air content. The next thing is to find out what the water to cement ratio is. This is kind of interesting. So, we need to consider both strength and durability. You just did a quiz and I asked you what is the effect of water to cement ratio on strength and durability. Water to cement ratio has a large influence on both, right? So that's why we need to take both into account. If water to cement ratio is very high, then your strength is low, porosity is high, that's why durability is also not very good. The material lets water in. So, based on the strengths, there are again tables where you can choose the amount of what you have to use for water to cement ratio. So if you are using air entrained concrete versus non-air entrained, then you have to choose something different. Now, I guess we don't have much time left. So you cannot just use the number that I gave you for compressive strength here directly. We need to manipulate it a little bit, and we don't have really time to go through it, so I leave it for Wednesday.